Okay, that's the first change. The second change is go down here because here it return integer. Go down here and then change this to add this, return 0. Otherwise we generate an error. Return 0. Okay. This one don't need to do. This one is you are supposed to do. Okay, ignore the bottom here. Only focus up to this point. Okay, put return 0. Okay, once you've done that, go up here, copy this. We want this to be added into our main as function prototype. Go to your main or your P3 CDP. My one I call it main. Go right at the top here. Add this here. I already did that. I have already here. Add it there. Now the second one, just ignore it first because you don't have it yet. Okay, only the first one. Okay, remember to put semicolon on the back there. Put the semicolon there. Okay. The second line here, just ignore it. I'll show to you later what to do. But at the moment, this one first. Okay. And inside your main file, main function. This is my main function. Add this. If you don't have it, add this. Okay, this is going to allow you to get the user input on the command line interface. We will learn this in practical 4, practical 3, practical 4, remember? We will learn this. At the moment, just put it first. Okay? Put that. So it's integer argc, comma, character 2 asterisks arg. Arg means argument. Alright? Now down below here, call this function. This one. P3Q3 argc argv. Okay? This one you can comment out already because we are done with it. Okay, we do this. Add this in. So you call the P3Q3, you pass in the argument. Okay, what do we pass in? I'll discuss this in practical 4. But at the moment, just pass this in. Okay, actually there's nothing in there. Okay, it's not very important. For this program, it's not really important. Okay? But in order to make it run, you have to put it. Okay, once you've done that, try to run the program. Compile it and run. Oh yeah, it takes some time. It takes 2 or 5 seconds to run. Doesn't look good. This one, yes. Okay. So you should get something like this. Order 1000 multiplication. Oh, actually it's not 1000, it should be 1000. Actually it should be 1 million multiplication. I think something is wrong here. The original author did not realize that it's it's order 1000, sorry. But the total number of multiplication is 1 million. Okay, 1 million multiplication, it is done in 2.5 seconds. How many million floating point operation? It is about 1 gigaflow. Almost 1 gigaflow. That means 1 billion. 1 giga is 1 billion. Right? So it's about 1 billion floating point operation in 2.5 seconds. Okay, so that's quite a lot of floating point operation. Okay? So we want to improve this performance. Okay, we want to improve it. If you have 16 cores, we want to improve 16 times faster. Okay? And of course GPU also has floating points operation. We can have more cores running at the same time. And GPU is very good at this. Okay, you can solve this even more faster than this. We will cover later in a short while. But we do this one first. First thing is, I want to, although your job is actually very simple, because of the pore reduction, you don't have to work very hard. Pore reduction is going to do it for you. We need to identify which place to put the pragma OMP pore reduction. Okay? But where to put and what this do, you have to pay a little attention because I want to explain now. The code is quite lengthy, starting from there and here. Okay, so it's quite long. Okay, so let's see what this code is all about first. Okay, from the text that you read just now, we know that is matrix multiplication. Right? So matrix multiplication is like this. You can visualize it like this. You multiply with another matrix, and then the result is another matrix. Okay, how about the size? The size is how many rows, how many columns. Okay, how many rows here? We got n rows, we got p columns, and then here we got p column, we got m, p rows, m column, and the result will be n rows, and then m columns. Okay, so like this. NP, this must be the same. PP, this can be different. Okay, and then the result here is this n, and then is this n. Okay, so that's how you remember. Okay, if you want to memorize, how you memorize. But normally I don't memorize. I look at how I actually multiply them and figure out what is this dimension and what is this dimension. Okay, let me explain to you. So this n here is how many rows that you have there. This p here is how many columns. The same thing. How many rows, how many columns, how many rows, how many columns. Right? And that corresponds to this n, d is dimension, p and n. Okay? But before we go into that, let's look at this first. Why do we need to do matrix multiplication? Why is it important? If you play games, everybody play games here, right? Play 3D games, right? Do you realize that the programmer that program that games have to deal with this matrix all the time? Okay, if you do not know, now you know. Okay, if one day in the future you suddenly want to become a game programmer, 3D game programmer especially, you have to deal with matrix all the time, all the time. Okay, and there are a lot of them. Okay, let's say for example, you see the figure, the three-dimensional figure that is moving, right? There are so many triangles there. All these triangles have to do this operation. All of them. You got billions of them there in order to make the 3D smooth. Okay? So that's one application. If you play games, you can understand why you need to do matrix multiplication or matrix operation, not necessarily multiplication. It can be addition, it can be division, but what we're going to study here is multiplication. Now, it's only is that the only place that we use? No, actually, it's everywhere. Okay, everything that you deal with, especially with mathematics, most of the time you'll be dealing with matrix. Okay. When I was younger, when I was a student, I was studying in secondary school, I always asked my teacher, I said, why do we need to learn matrix? And I hate matrix so much. So I did not study that well. I'm good in other mathematics, but I'm not good in matrix because I refuse to study, because I don't see any importance in it. And my teacher also cannot tell me why is it important. I only realize it when I study in my college study, and when I went to do my PhD, I had to deal with matrix all the time. Okay, then only I start to study seriously. Then only I realized that it was important. Okay, now I was doing optimization, and I had to deal with this actually I was doing traffic engineering. I have to do a lot of optimization, and every time I deal with optimization, I have to deal with matrix, right? And the number here is a lot. It's going to be billions of row, a couple of millions column. So it's a lot of operation to do. That's why we use paracomputing, because otherwise it take a long time to compute. Okay. And what other use of it? You go to hospital, you do CT scan. Anybody here have done CT scan before? But maybe you have heard. What CT scan does is actually slice, virtually slice, actually not physically slice, virtually slice you, so that it can view your internal organ in 3 dimensions, right? In order to predict how each slice looks like, you have to put it into matrix. Okay, so basically what this matrix is a lot of equation there. There are a lot of equations. So this row here is the number of equations that we have. The column here is the number of variables that you have. Okay, how many variables that you have? This is how many equations that we have. So basically it solves equations. That's why we use it in a lot of different places. In tomography, in CT scan, in three-dimensional games. Okay, in my field, I also use it. In AI, also use it. AI also use it. Big data, you might use it as well. If you have data science, you'll be solving a lot of equations. You have to use it. You have no way to run away. Okay? Maybe you think that you can run away. Actually, you cannot run away because you have multiple equations you have to solve. So basically, this is the basic one. Right? The basic thing that you need to do is multiplication. Okay? Of course, to solve the problem, you have to do the inverse first, then you multiply. When you multiply, you got the solution. Okay? The solution is the answer that you are looking for. Okay? And now we are going to solve that problem. Okay? Here we solve using single thread, and we want to make it faster. We use multiple threads, okay, or multiple cores. And of course, with CPU, it's fast, but then it's not fast enough. And later on, we're going to switch to GPU. Okay, with GPU, we're going to solve even faster. Okay, so what is this order? This order is the number of either the number of variables or the number of equation that you have, or the rows. Okay? In this case here, we fix it at 1000. And you can see that all of these dimensions, N, P, and M, have the same order, they have the same dimension. So 1000, 1000. Let me see 1000, 1000, 1000, 1000. Okay? Now, just like I mentioned to you, here is N, this is P. Because of this P, this must be P. Okay? Why is that so? I'll explain in a short while. And this is N. Now, because of this N and M, that's why here must be N, and this must be N. Okay? So, why is that so? I'll explain it now. Okay, the reason is because when you multiply like this. So here is P number of elements, and this is also P number of elements. So this P columns, P rows. Why P and P? Because when you multiply like this. You take this, you multiply like this. Okay? And then you add the result with this, multiply with this. Okay, and then you add the result with this, multiply with this. So if you have P, here must be P, because you have to multiply the same number of elements. Okay? Now the result of all of this sum is going to be placed here. Okay? Now the same thing for the next column here. The next column here actually comes from this column, not from this column. So what you do, again, the same, take this, multiply with this, okay, add it to the result of this multiplication, add it to the result of this multiplication, and so on and so forth. Now once you have done, the result of this multiplication and addition is placed here. Okay? So how do I know that is that? It's because row 0, column 1, row 0, column 1. Okay? So if you continue on, you can see that this is m row, and therefore this must be m. That's why this m must coincide. Okay? Now how about the bottom here? Where does this come from? This one comes from the second row. Okay, the second row. You take the second row and you multiply with this first column. You multiply this with this, add with this, add with this, add with this, and so on and so forth, and then you get this. Now how granular is this? Because it's the second row, okay, and first column. The first column is the second row. Right? Now if we continue on to n row, then that's why here is n row. Okay? So that figure 10 and n come from this n and this n. Okay? This p is because they must be the same dimension. Right? Okay? But here the problem is much simpler because all of them are the same. So n is equals to p is equals to n is equal to 1000. That's what this tree line is all about. Okay? Now, when we want to solve the problem, of course, we need the data, right? But where the data come from? First thing is you have to load the data into the memory first. So, do we have the memory? At the moment, we don't create any static memory. So we create a dynamic memory. We use malloc. Malloc means memory allocate. Okay, we allocate dynamically. And what is the size of this? The size of this is n times p. So this one is n times p. This is A, matrix A, matrix B, matrix C. Okay? So n times p times size of double. Why? Because each element here is double. So we want to find out how many bytes to allocate. Double is 8 bytes, so 8 times n times p. So that is the number of bytes that you need to allocate. Okay, so malloc actually takes in the number of bytes that you need. Okay, you allocate the memory and it passes back a pointer to you. Okay, you give you an address, and this A is a pointer to double, so you point to the first element. Here, so you point to here. Your A is going to point here. Your B is going to point to the first element as well. The first element is here, 0, 0. This C is going to point to the first element. Okay? Because the rest of the element can be found from this first element. You can offset it and then you can find it, right? Okay, so that is these 3 lines here. Okay, now how about the next portion of code? All these for loop. So what are they? We look at the command. It says initialize the matrix. So what does it do? We have 2 for loop over here. What does it do? It will visit each of this element. This is J. J. This is I. Okay. You move like this, J, and then you go down, J, you move down, J. So that's the reason why we got 2 for loop there. Okay? And for each of this set of this for loop, you initialize all the element to A val. So let's look at A val. A val is 3. B val is 5. Okay? A val is 3. Is 3. So basically, it initialize all this to 3. Okay, you initialize to 3. Now the second one, also the same thing. Okay, I is this, J is this, so it goes like that. The first for the inner for loop move like this. The outer for loop move to the second row. Okay, so it will do like this. And what does it update? It update B val. B val is 5, so it's going to be 5. So all 3, all 5. How about the next one? The next one is for C. Okay, the C is the same thing. I here, J there, and then you move like this. And every time you move, you update to 0. So basically, you are clearing all this to 0. Okay, basically you're going to multiply and then you're going to put the result there. Put the result into there. Okay, actually this last one is not really needed because later on you see that when you multiply, you put into a temporary variable and then you override it. So this last step is not really important. But here it shows to you that you can choose to clear it, but it's actually a waste of time and waste of processing power. Now, let's look at this code here. This one looks very scary. What does it mean there? But before we go into that, I'm not sure how strong your C++ or C program. I know all of you learned C program before, right? C or C++? Maybe C++ or C. It doesn't matter because here applies to both C and C++. Okay, it's just a short review of your C and C++ pointers. You can see you got integer A, 5, integer B, 6, and then you got pointer to integer. And let's call it PTR and the address of A. What does it mean here? Okay, this is just a short review because I want to explain that. I need to make sure that you all understand before I explain first. So how does it look in the memory? Now, every time when you see this, trust me, you want to visualize it. Because if you don't visualize it, it's very hard to understand pointers. Okay? This is how I visualize it. Whenever you see this, the compiler at the back end, you will assign a memory address to this A. Let's assign it. I'm not sure what the compiler will assign. Maybe assign it to 100. Okay. Now, in the end, who actually assigned the address? Actually, it's the operating system and the compiler will assign the address for it. Okay, it's a two entity that is going to assign the okay. But here we assume that the compiler assigned this. Okay, 0x10. And what is inside there? We initialize to 5, no, it will be 5. Okay. And B, again, you create B. And let's say this address that is assigned by the operating system and the compiler is 700 and it's going to be 6 because it initialized to 6. Now how about the PTR? The PTR is going to be here. It's also a memory. It's called PTR. It's just the same memory, just like the rest here. Okay. It has some memory as well. And then it has certain address. Let's assign address, I'm not sure, maybe 100. Okay, and then address. Okay, but the content here is different. This content here we know is type integer, so we know that it must be integer. Right? If it is character, it will be character. If it is a string, it will be a string. But here it's integer, it's very clearly specified it's integer. But here, this is not integer inside here. Not integer. What is inside there? It's the address. Why is it the address? Because it's a pointer. This is how you read it. PTR is a pointer to integer. Is how you read it. Okay? If you have two asterisks, it means PTR is a pointer to integer. Okay, that's how you read it. In this case here is a pointer. So whatever content inside here is the address. It's not integer, it's address. Okay? That means if I want to assign something into here, I must assign the address. That means I cannot do like this. If you do this, the compiler will complain. Will tell you that, no, I cannot do this. Why? You're trying to assign 5, which is integer, and you're assigning into the address. This address is not integer, so it cannot accept. And so the compiler will refuse to compile. You say that you have to fix this. Okay? Now how do you fix it? Easy. Just put ampersand there. Why? Because ampersand means the address of A. Right now, this is the address. So this address is placed inside here. The compiler is going to be happy. Why? Because the content here holds the address. So the address of A is not 5, it's this address. 0x100. And why is that so? Because this is a pointer. Why? It points to something. It points to where? It points to here. Is it correct? It does not hold integer, it holds the address, and this is where it points to. That's why it's called pointer. Point to something. Point to what? It points to this A, and this A is integer. The type must be the same. Okay? Right, next. If I were to change this value, 5 to 7, how do I write? I write like this. Then when I execute this, this is going to be changed to 7. So this is called direct access. I access into A directly using the variable name and I change the value. Now I can access this variable using indirectly, using pointer. Because my pointer is pointing to A. Now I can use this pointer to change this value to some other value. Let's try. This is how I do it. Dereference the pointer, PTR. I change it to 18. Okay, so what does it mean? Now this asterisk and this asterisk is different. This is declaring this PTR as a pointer. This one, it means dereference. Dereference means you start from here, dereference this address, and now we're here. Take this 18, replace it. It means that. Okay? So if you see this, imagine what I mentioned, that's easier to understand. Okay? Dereference, you see the first pointer, dereference, one time, goes to that, take this value, put in there. Okay? It doesn't mean that take this 18, put inside here, no. Dereference first, take this value, put in there. So this is indirect access into A. Okay? Now why do we want to do this? Because pointer is flexible, you can point to anywhere, right? So suddenly I change my mind. I don't want this pointer to point to A anymore. I want to point to B. So I do like this. PTR equals to the address of B. I can do something like this, right? Okay? Take note, I don't have asterisk anymore. Don't have asterisk means I don't dereference. I put it in directly into this content here. Okay? What do I put inside here? I will put the address of B. The address of B is 700. So this is going to change to 0x700. Because I put into the content. I don't dereference, I put into the content directly. So right now, this is no more pointing there. It's no more pointing there. Where does it point to? It actually points to there. Now, if I change the value, I dereference PTR, and I change to 35. Okay, here actually change this 5 to 18. This one, does it change this to 35? No more, because it's pointing to somewhere else now. It's pointing to here. So when you dereference, right now, if you dereference 700, that means you go to here. 35, put it in there, this will change to 30. Okay, the reason why we use pointer is because the pointer can point to anywhere. Okay, the code is the same. We don't change the code. We only change where the pointer points to. And that's why it's flexible. Okay, that's the reason why we use pointer. Okay, let's come back to here. For the same reason, we use pointer so that we can move this pointer. Okay, we can move the pointer. You remember I moved the pointer? My code is the same, no different. Okay, you can see the same, but my pointer moved. Then I can initialize the value. That's why we use pointer. Okay, so let's see how we do it. Oh, we don't have time really. Do you have class? Actually, I have class. The students waiting there. Okay, I do it very quickly. Okay, so let's see the memory. When you allocate a memory, we visualize its 2 dimension. But actually, when we allocate the memory up there, we allocate a linear address. So the address looks like this. What is the size here? The size here is this P. And how many times here is this N? Okay? So this one corresponds to the first row. This one corresponds to the second row. The third row is here. The fourth row is here. So it's linear. Right? Here my coordinate is I and J. So I need to convert this ij into linear address. So here, this location here is I multiplied by PD. Okay? Sorry, I shouldn't do that. Let's see here. Okay, this here is plus the offset J. Because the offset J is starting from 0, right? So 0 is 0, 1 is 0. Why PD? Because this PD. Okay? This I0, this is I1. I1 multiplied by PD is PD. This is correct. Okay. PD plus, let's see, J is 2, is 2. Okay? So if you look at this equation, isn't it the same as this? Same there. Right? Plus A, why A? Because my base is A here. You see A becomes the first element. Here is A. Starting from here. Alright? So this applies to A, applies to B, applies to C. Okay? So if you understand this, then it's easier to understand. Because down below it's even worse. See here. But if you understand what I say there, you look at them, they are the same. See? Same. Okay, you understand the talk, right? You should be able to understand this. Okay, I'll explain this one later. This one actually is assessing this. And then place it inside C. Let's see that C there. Okay, it's this one. Alright? Sorry, this 2 here is actually assessing this element. You're multiplying this. Okay, that is this line. Okay, I'll explain this next week because I have another class. I also think that another class. Before we go, I need to take attendance. Before you go, save it first. Make sure that you save when you come next week. I hope that you can do at home first before you come. Li Hui Wen, Chan Chen Yu, Chan Zi Zun, Chan Zuoyan, Chin Junjian, Emerson Hu, Jasper Lee, Ko Yayu Yu, Lai Xiaozian, Li Yihan, Li Ziha, Lim Juntan Peng, Ling Hui Shan,